Good evening, participants. Welcome to the webinar on Unveiling Misconceptions, How AI's Questions Drive Conceptual Understanding. Today we have Diksha, my colleague from the maths team, and myself from the maths team again, who will take you through what are these misconceptions we have found in our work through asset questions and cares questions, through student interactions, and enlighten you with some of these insights that we have gathered. Some of the norms for the participation. You can enter your questions in Q&A. We definitely would like to have you engaged and feel free to participate, ask us questions, but only enter your questions under Q&A and not as chat message. You will receive a certificate of participation automatically once you complete filling up the feedback form at the end of the webinar. So please ensure your details are correct. Okay. Does teaching always imply desired learning? I find this cartoon strip not just amusing but even enlightening. What it says is, I taught Stripe how to whistle. So he has taught this Stripe how to whistle. I don't hear him whistling. I said, I taught him. I didn't say he learned it. Right? Knowing what students have learned and what they have not learned is definitely a rewarding experience in long term. While it may come with short term pain, I have taught so much and still they haven't got it. Maybe that will be short term pain, but I'm sure you will find it much more rewarding in long term. We are happy to share our learnings with you in the next hour based on questions from EI Asset and EI Cares, and as I said, from interactions with them. We will take you through what are misconceptions, where they stem from, why it is important to learn, what are these misconceptions in certain areas, and what are the best practices for us as educators to remediate them. Let's compare the two questions on screen. Which of the two assesses the conceptual understanding of the angle sum property of a triangle the best? The one on the left or one on the right? For the entire webinar, the examples are just representative of the key messages. So let's focus on the key messages being driven through them, not too much into the examples themselves, which grade they are in, what concepts, and things like that. Okay, so when we ask these questions to educators like you, we have always seen the responses, the one on the right side. The one on the left side is routine question. They just have to plug in these numbers in angle sum property formula. Angle A plus angle B plus angle C is 180 degrees and they will find the remaining angle. But the one on the right will make them think. Irrespective of what the type of triangle is, the sum is always going to be 180 degrees. That is what we have taught them. And we will be amused to see what they respond. One of my colleagues will actually take you through that. What's this response and what's the extent of wrong notion students have. Students are expected to answer as sum of measures of three angles is the same in each of the three triangles. But we found the most common wrong answer option is triangle 2. For them, that is the one which has the greatest of the sum. Do students answering as triangle 2 have some underlying belief or wrong notion? Maybe let's think about that and revisit it once we get to the actual discussion on the same. There is indeed some underlying belief. Which of the two questions on the screen give us better understanding of what student has learned and what a learner has not learned? Why? Traditional definition, they can recall. The typical example that one would see that students will give is the one like shape 3, because that is a stereotypical representation they mostly see. The one on the right will stimulate their thinking. Is shape 2 also trapezium? Indeed. Is shape 1 also trapezium? It is just rotated. Changing orientation of a shape doesn't change the shape. So shape 1 will also be trapezium. And shape 4 is indeed trapezium because it has one pair of lines parallel. But we find students think that shape 4 is not a trapezium. Some students think shape 1 is not trapezium. Can we say students who got it right have desired conceptual understanding? Indeed so, because they are recognizing shapes based on their properties and not the mental image of a shape. That is what is expected of them in higher grades. This question is from grade 8. Can we identify a good question as good if it gives more information on what students have learned and what they have not? That should be one of the criteria to say a question is good or not, as per our belief. What do you say? Think about that. Why would students answer only shape 1, 2, and 3? What is the underlying belief? Do such questions give insights into what students have not learned? What is the undesired learning that they are demonstrating? Indeed so. Here in this case, it is trapezium cannot have a right angle. That is a false belief they have, but that is not desired. Some students think after rotation, shape is no longer the same. That is again undesired conception or undesired alternate conception. In our data of grade 8, we found that only 28.6% of students could get it right. 52.2% students selected shape 1, 2, and 3 as trapezium and not shape 4. What information are we getting about their level of understanding from the question? One is complete absence of understanding in case they cannot answer the question. The other case is desired understanding. All 4 shapes are trapezium. And somewhere in between, students might be having partial understanding. In that scenario, some students will only identify shape 3 as trapezium. Some students will identify shape 2 and shape 3 as trapezium. And some will identify shapes 1, 2, and 3 as trapezium. So when they have partial understanding, they could be in any of these states of learning, levels of understanding. And one can see the gradation, how close it is to the desired understanding. This is B1 is slightly away from the desired understanding. So do students answer responses in form of B1, B2, B3 have some underlying belief? Yes, indeed. What are these beliefs? Right? We just spoke about that. What information one gets on students' level of understanding with a good question like this? What would students of grade 6 commonly answer over here? In our journey, we found 7 centimeter and 6 centimeter were the most commonly answered wrong options. Across students of grade 4, 6, and 8, we saw that pattern. Why would students answer as 7 centimeter? Because pencil ends at 7 centimeter. They've just the belief that wherever the endpoint lies, the mark corresponding to that is the length. Why would students answer as 6 centimeter? Any guess? Are these students answering this in hurry and hence a careless mistake? Often when we bring this data to educators like you, we find that is what they feel. But that's not the case. Let's see what exactly happens. Why?
1, 2, 3, 4, 5, 6, 7, 8.
So you counted that and that's why you said that
Yeah.
it's 8?
Yeah.
And not because this point is 8?
No.
This 4 will count as 1 and till 9 it will be 6. This is 1, 2, 3, 4, 5, 6. We'll not see how much there is.
Starts from 6 because it starts from 4, 4, 1, 1, 2, 3, 4, 5, 6.
This to this is 1 centimeter.
Yeah.
And this to this?
That is 0 centimeter.
This is 0 centimeter. How much is this to this?
2 centimeters.
Okay, so this much is 2 centimeter?
No. Yeah.
Okay, and how much is this?
5 centimeters. My name is Yash and the answer is 6 because it's starting from here. 1, 2, 3, 4, 5, 6. And the ending point is here.
Right? So we saw that students who are answering as 6 centimeter, whatever they are answering, they have strong rationale behind it. It's not necessarily a careless error or a slip. Right? Is it that only a few students have this misconception or alternate belief? Not necessarily. The data from English medium private schools in 5 metro cities from popularly seen as good schools share with us that about 30% of students of grade 4, 6, and even grade 8 answer as 6 centimeter. They are counting division marks. So this was really amusing and really enlightening to us that the misconception is not going on its own. It persists even in grade 8. What are the 3 primary states a learner could be in while learning a concept? Let's imagine this in the context of this example of ruler measurement. So absence of knowledge could be one state. They cannot measure the length of an object using a ruler. Second is the demonstration of desired understanding. They can measure length of any object using a ruler in any situation. And third could be intermediate state of learning or partial understanding. That is the state where students may be having alternate conception or misconception. And that is of interest to us. I understand you are among League of Educators who just do not want to teach. You really are interested whether your teaching has led to the desired understanding or not. That's why you have joined us today at 5 p.m. in spite of being a weekend, right? Hence, studying about misconceptions is definitely of interest to all of us, which will help us make students learn the desired. So here, 6 centimeter is the alternate conception or misconception that represent that answering by 6 centimeter is being represented. They are basically counting division marks, and to them, that's what is about measurement of length of an object. Whenever students are answering any question incorrectly, to summarize, they could be demonstrating absence of knowledge. Maybe in some cases, they are making careless error, and mostly they would be having some alternate notion, that is misconception. How do we distinguish between slip and misconception? We feel if we ask the question in any form, and if they consistently demonstrate the same pattern, the same rationale of answering, that would validate it. For example, if they are counting division marks over here, in this version of the question also, they will demonstrate that and say the answer is 6 centimeter. Often it helps to ask students to justify their answer. Let's get into another video.
In the world.
College students of premier institutes, the Ivy League universities.
Do you think you could light a bulb with a battery and wire? Do you think you could light a bulb with a battery and wire?
Yeah.
Light a bulb with a battery and a wire. Maybe. Yes.
All right.
Definitely.
Do you think you can light a bulb with a battery and a wire?
Battery and wire? Well, yes, why not?
Okay.
Definitely.
Okay. Can you do that?
The interesting part about the batteries and bulbs question is that people always predict that they can do it. Students say, of course I can do this.
Any hints I should have here?
Teachers say, of course my students can do this.
Ow! Do you know why that didn't work?
I have no idea.
Battery could be dead, the bulb could be bad, I'm hooking it up totally incorrectly. I'm not an electrical engineer, I'm a mechanical engineer. But if I had to guess, I would say it's operator error.
Okay.
I know it's possible, but I don't know how to do it.
It's only after failing that you begin to get upset with the question and think, well, maybe it's a trick question, maybe this has something to do with manipulating the wires, they couldn't hold all the wires together.
You don't have a current if you only have one wire. You need a closed circuit.
But that's not the case.
Well, if I do it with a little light bulb, I just do this. In which case, the light just lights up.
It goes to the fundamental understanding of electricity. If one cannot light a light bulb with a battery and wire, then everything built upon those basic ideas has problems.
We've always assumed that if teachers teach, students will learn.
Right? So that's the power of good question. It can stimulate thinking. It can lead to construction of new knowledge. It can elicit whatever wrong notion or alternate belief students have, which is not the desired understanding. So often EI asset questions or EI cares questions, which we are going to project on our screen, and subsequently when you find them in those reports, might tell someone that maybe these are tricky questions. That's natural. That's the story with many of the questions diagnosing misconceptions. We need to challenge and stimulate thinking with such good questions. This is the greatest inspiration for us at EI when we create such questions for EI Asset and EI Cares. We are happy to showcase them and the insights we have gathered through this. So to summarize, teaching doesn't always imply desired learning. There may exist a gap between what is taught or facilitated and what students have understood. We would have taught them the definition of trapezium is quadrilateral with at least one pair of opposite sides. But what students have understood is this. Whether it was intentional or unintentional, that is what students learn. That's because students always learn from their own prior understanding, and each learner brings different prior understanding. Can we say students who got it right have desired conceptual understanding? Indeed so. What's the learning gap or misconception? To reiterate, that is trapezium cannot have a right angle. When you rotate a shape, it's no longer the same shape. And most importantly, it tells us that students are not recognizing shapes based on their property, but more from a mental image of a shape. And they need to make this shift in learning of geometry when they move to grade 6 and beyond. So let's get into what are misconceptions and their sources. Misconception is an undesired understanding a learner has. So assuming a question is perfectly fine, free from any errors, one of the things could be slip or careless mistake when they are answering. Let's even rule out that. Then what it demonstrates whenever they get it wrong is that they would be exhibiting some sort of procedural error. For example, in finding the sum of half and 3/4, they might arrive at the answer 4/6. In case of answering of this question on equal sign, student often give 5 as the answer. Now that is not a procedure, in spite of this asking them to find a sum. That is conceptual flaw that they have. What is that flaw? In their mind, equal sign means answer of the expression to its left. It's not about the two expressions on its either side are balancing. It's not 2 plus 3 is the same as 1 plus 4. Right? So that is what we mean as misconceptions. It could be in procedures, it could be in concept. And good questions which elicit conceptual understanding often elicit misconceptions as well. Like this. Which angle has the greatest degree measure? That is what we asked. The expected correct answer is option B. Only 51% of the students could get it right. 31% of students answered as option C. Why? Because according to them, angle measure is nothing but length of the arms. For some of the students, angle measure is the area enclosed between the arms. So area is most in all of the shapes, all the given angles over here. Hence, to them, the angle in C has the greatest measure. The length of the arm is shortest in this case, so they don't feel angle in B is having the greatest measure. Right? So these are the two different misconceptions students might have related to angle measure. And that is undesired understanding, faulty notion about the concept. Why do they arise? This is happening because whenever learner is learning a new concept, he is building from prior knowledge. He has to make appropriate connections between the new idea. So all these blue dots are existing ideas that students have already have in their mind. The red dot represents a new idea being developed in their mind. They have to make appropriate connections. These misconceptions arise because these connections are not being made appropriately. Some of the connections are not made. The more richer these connections are, the better the understanding students have. So just to summarize, when students are learning, they are learning based on their prior knowledge. Every learner brings different prior knowledge. And it's natural in acquiring new concept. Some of the students will have these misconceptions. Hence, it is of great importance for us to uncover them, to know about them. Often these will manifest from these primarily three areas. One is they will use prior knowledge incorrectly to learn a new concept. Sometimes they overgeneralize the prior knowledge or rules. Sometimes they apply the rules where they shouldn't have been because they don't know where these rules work, why they work. Let's say in this case, this is because in inappropriate use of prior knowledge. In case of length measurement, they've understood wherever the endpoint lies, that is the length. They will use the same understanding and extrapolate that for angle measurement as well to answer as 145 degrees over here. In this case, students think that the ratio of shaded area to the unshaded area is 1:2 even for this shape, the last one. That is because they don't understand parts need to be equal for the ratio to be 1:2, and that may be stemming from the underlying problem that they have for fractions as well. They think shape in 3 is also 2/6 shaded. Here in this question, student is asked that when a ball is dropped, the water level has increased. They are expected to know whether amount of water is the same or not. So when it is 2 liters of water in earlier case, after dropping ball, the container will also have 2 liters of water. Only 23.3% of students could get that. Most students said that it will be more than 2 liters of water now. Where is this stemming? They know that greater water level corresponds to greater amount of water. They also know that water level go up when object is dropped into the container. And incorrect connections are made in these two ideas to be able to answer it right. So that's how the faulty connections with the prior knowledge has led to the wrong underlying belief over here that amount of water has increased. In this case of question on ordering of decimals, students are expected to say that 1.08 is the shortest length. Hence, this is the insect with shortest length. 46% of grade 6 students said it is 1.3 centimeter. Why? Because they are ordering like whole numbers. They are saying 3 is smaller than 0.8, which is 8. So 1.3 centimeter is less length than 1.08. They are inappropriately applying ordering of whole numbers to decimals as well. So that is overgeneralization of ordering of whole numbers. By the way, that strategy works when you convert them into like decimals, 1.30, and then 30 and 8 can be compared. So maybe that kind of rule is not understood when to apply. Students answer in this case area of trapezium as 44.62 by putting side lengths of PQ and SR and taking altitude on them. Now these are non-parallel sides and altitude on them is on non-parallel sides. The formula demands them to substitute for lengths of parallel sides, which is PS and QR, and altitude on them is QM. Only 1/3 of the grade 8 students could do that right. Grade 9, sorry. And 28.7% of grade 9 students said 44.62. Why? Because they are faultily applying the rule or formula, and they have failed to understand where the formula works. So we have seen this pattern. Generally, students mechanically plug dimensions. And why? Because we educators and textbook examples only give them the dimensions that are required. Only when we ask questions like this, they need to figure out what lens to use, right? In real life, whenever we are solving a problem, we are not given only the thing that is desired, which is required to solve a problem. We have to identify what information we need. In this case, students are identifying angle marked as X and this one as corresponding angles correctly, but they are over generalizing or faultily applying the rule that corresponding angles are equal when angles are formed across parallel lines. Here lines are not parallel. 34% of students fail to realize that the property holds true only when corresponding angles are across parallel lines. They said x is 110, x is equal to 110. That is, corresponding angles are equal. Why it is important to know and address these misconceptions? Let's understand with one more example. When we ask students about ordering of decimals, they or exhibit any of these three faulty understanding or misconceptions. As we saw earlier, students compare as whole numbers. Some students who are into getting into desired learning overgeneralize certain rules. For example, in this case, second one, they think 8 tenths and these are 75 tenths. 8 tenths is less than 75 tenths. So they say 4.8 is less than 4.75. There are some students who say 5.32 is greater than 5.736. Why? Because they see this as 32 hundredths and on the right 7,736 thousandths. Any number of hundreds is greater than any number of thousands. Now that is the correct notion, but they are faultily applying over here. And they get 5.32 is greater than 5.736. Now, what is interesting is that in spite of faulty thinking, in some scenarios, students will get their answer right. So 7,036, 62. Indeed, that 736 is greater than 62. So this number is greater than 5.62. So in spite of having faulty understanding, they get this pair right. Similarly, students have faulty understanding with respect to comparing as hundreds. They will get these four questions right. So underlying message is basically, in spite of faulty understanding, they will get some questions right, which is reinforcing their understanding. And such misconceptions persist even beyond grades 5 and 6, like the case for length, like the case for decimals over here as well. Now, these faulty understanding or misconceptions impede learning of higher concepts as well. If, for example, of length, it will show up in angle measurement as well, and later on other measurement concepts as well. A learner is often unaware that he has this flawed understanding. It is only when we ask these questions that that wrong notion will surface and will be made cognizant about that. And as I said, the faulty reasoning may lead to correct answer, and that is reinforcing their understanding. And that faulty reasoning then gets deep rooted. Very resistant to instructions, often because of that. Generally, ordinary form of instructions like lecturing will not lead to successfully overcoming those deep-seated student misconceptions. My colleague will now take you through some examples of misconception questions and help you understand what all different faulty understanding students have in different domains. Reflect on the strategies you will use now to teach in classrooms now that you are aware of these misconceptions.
Thank you, Maulik. I hope I'm audible.
Yes, you are.
Okay. All right. So in this segment, we will try to cover a few types of misconceptions, their extent, and how it affects later learning. We will try to cover misconceptions in three main domains, that is number concepts, geometry, and mensuration. But I would like to say this as a disclaimer that these are not the exhaustive domains. Definitely, we have a lot of domains in mathematics where there are misconceptions and faulty understandings. But in the interest of time, we have restricted to three domains. In future webinars, we'll try to cover more and diverse domains. In each of these domains, we'll try to cover a few types of misconceptions, their extent across classes, and how it affects learning. So misconceptions in number concept. Number concept as a skill refers to the foundational understanding of what numbers are, how they work, and how they relate to each other. For example, if I ask you to add 42 plus 39, what do? We do 40 plus 39 plus 2. Number concepts are fundamental to mathematics. Let us look at questions one by one. Look at the question on the slide. What number is R likely to represent on the number line? So we all know that R is between 3 and 4, exactly halfway between 3 and 4. So that makes it 7 by 2. 7 by 2, option D is the correct answer. But shockingly, if you look at the data, so, okay, one more thing I want to share here is all these data are actual real data we have taken from EI asset. So you might be aware of asset EI asset. It is a diagnostic test that EI offers. So all these data are taken from EI asset reports. Okay. So option D is the correct answer, but you can see that 52, almost 52% students have gone for 3 by 4. Also 23.9, that is almost for 24% have gone for option A, that is 1 by 2. Now, why students may have gone for 3 by 4? It is because it is between 3 and 4. What is the underlying misconception is, so a fraction between A and B is A by B. So that is the main cause of this misconception. Now, how can you as teachers, how can you address this during your teaching? So say for example, show them where 1 by 2 is, show them where 2 by 3, 3 by 4, 4 by 5. So in general, show them where n by n plus 1 is. That way, they will realize that all such numbers are between 0 and 1, right? So this is one of the strategies that maybe you can try out in your classrooms. And we also saw here that option A, half, has got 24% performance. Why students might have gone for that? Because it is half of 3 and 4. They know that between 0 and 1, the point which is exactly between 0 and 1 is half. The same overgeneralization has taken place. They have generalized that to the number which is exactly in between 3 and 4 as well, half of 3 and 4. Moving on to the next question. So this is a question that tests the application of rules of exponents. Minus 1 to the power 2010 plus minus 1 to the power 2010 is what? So what is the correct answer? Correct answer is, since the power is even, first term becomes +1, second term becomes +1, +1 and +1 is 2. Option C is the correct answer. But 44% students have gone for option D. What are they doing in option D? They're adding the base of both the exponents. -1 -1 is -2, and then raise the power to 2010. What could have been led to this faulty understanding? There is a rule under exponents, multiplication rule, which says a to the power b times c to the power b is ac to the power b, right? So students have applied an incorrect law, incorrect formula in this context. So basically, they are not able to identify what to apply in this context. This question is not at all difficult. It is very simple. You can simply simplify the first term as +1, second term as +1, and the answer is just 2, right? But they are trying to apply exponents rule where it is not required at all in the first place, right? Okay, moving on to the next question. A1 Airlines increased their fares by 10%, but due to decrease in the demand, they had to reduce the fares by 10% of the increased fares. The resulting prices are dash the fares before the increase. Now, what is the answer? Initially 10% increase, and then 10% decrease on the increased price, which will lead to the resulting price being less than the fares before the increase. But you will see that 48% students have chosen same as. What has happened? They think +10 increase and -10, which is decrease, cancels out. What is the problem here? They are not accounting the base each percentage is applied on. First percentage was applied on the original base, but the second percentage change is applied on an increased base, right? So students are not able to understand the significance of the base while calculating the change in percentage. Okay, moving on to the next question. So next domain, in fact, is geometry. All right, this is a very interesting question. Let us take a look. Afzal has made a square on his computer screen. He now turns the shape as shown. What is the change in the shape? Now, as we are all teachers, math graduates, we all know that merely rotating a shape will not affect the properties, intrinsic property of the shape. So it will still remain the square, right? So the expected answer is option D. The figure remains a square and there is no change in its side, as there is no change in its side. But 53.7% students have gone for option B. And what it is? The square changes into some other shape, but its side lengths don't change. Now, what is happening here is students are not able to identify the shape based on the properties of the shape, but they're merely going by the visual change or visual recognition. This is because they have learned the shapes just visually, and they have not learned the properties which make those shapes like squares, rectangles, rhombus, etc. Right? It is important that these nuances are inculcated among students. This identifying the shape not merely by the visual recognition, but by the properties upon which they are built upon. All right, moving to the next question. My colleague showed this question to you in the first segment, and he told that we'll be seeing more about it in the upcoming slides. So again, What has happened here? We have asked them about the sum of measures of the three triangles being greatest. And we all know that all three have same 180-degree angle sum property. But 33.5 students have gone for option 2, which is obtuse angled triangle. Now, what could have been the reason for them going to option triangle 2? It has the largest angle among the three. Among the three angles within the triangle, it has the largest angle compared to triangle 1 and 3 because it's an obtuse angle, right? But still, the sum of the three angles will remain the same. This has not trickled down into students' minds. That is why they are committing this kind of mistakes. Moving on to next question. This is about congruence of triangles. In which of the following pairs are the triangles definitely congruent? What is the correct answer? Correct answer is option D. You will notice that there is ASA straightforward in the first triangle of option D. But in the second triangle, there is a small trick. So we have given the other two angles, but using angle sum, third angle can be found to be equal to 65 and hence ASA. By ASA congruency criteria, option D is the correct answer. But 41% students have gone for option C, which has 60-degree, all three angles 60-degree, making students think that all equilateral triangles are congruent. Now, this is one of the major misconceptions students have, that all equilateral triangles are congruent to each other. Similarly, if you see option B, 25.6% students have gone for, they think that all right angle triangles are congruent, or maybe they have seen that the hypotenuse of both the right angle triangles are same, 10 centimeter. So they think that both of them are congruent. Now, what could have led to this? Number one, students incorrectly relating AA similarity criteria for congruence criteria. They think that AAA criteria is applicable for congruency, but it is not applicable for congruency. It is applicable for similarity. Now, as a teacher, what we can do? So whenever we introduced the concept of similarity and congruency, whenever we are teaching similarity and congruency, we need to distinguish between the two concepts. What similarity means, what congruency means. Take, for example, equilateral triangle. Try or help them imagine shrinking and expanding equilateral triangle. Tell them that equilateral triangle, if you shrink or expand, the angles will still remain the same, 60, 60, 60. But are they congruent after shrinking or expanding? No. So this is the difference between similarity and congruency. So this is one of the strategies maybe that you can use in your classrooms to distinguish between similarity and congruency. Next, we have the third domain, which is mensuration. Very important domain. We have seen a lot of misconceptions in these domains, mainly related to area, perimeter, surface area, volume, etc. We'll see a couple of questions. Look at this question, very interesting. Shown here are three shapes drawn on a paper. Which of them has an area? We are merely asking which of them has an area. We are not even going to calculation nitty-gritties of all finding the area. We're just asking which shape merely has an area. Now we all know that all three shapes have area, right? Because they're all closed shapes. All three have area. The correct answer is D. But 23.8% students think that only shape 1 has area. According to them, only standard looking shapes like square, rectangle, polygons have area. 31.3% students think only 1 and 2 have area. That means for them, only shapes with linear boundaries or straight line boundaries have area. So what we did an interesting experiment. We asked this question in 3 classes. Same identical question in 3 classes, 5, 6 and 7. Now there is a graph on the screen. It is an item response theory graph, IRT graph. I'll not go into how this is obtained and all that. We'll just quickly see what it tells us. Now, the orange line on the graph corresponds to the misconception that only basic shapes like standard looking shapes have an area. Interestingly, you will see that that particular misconception has increased from 5 to 6 and then decreased in class 7. This is very interesting to see that more proportion of class 6 students think that only basic shapes have an area than class 5 students. Very interesting, see? And the red line corresponds to the misconception only shapes with straight edges have an area. You will see that that misconception has gradually decreased from 5 to 6 and further decreased from 6 to 7. But there is still large proportion of students who think that only shapes with straight edges have an area. That is why the red line, the red graph is upper in the graph, right? You will see that it is in the band between 20% to 40%. Almost, even at class 7 level, almost 30% students think that only shapes with straight edges have an area. That means even though the extent of misconception is decreasing, but still there are a lot of students who think or who have that misconception in each class. Similarly, green line shows the extent of correct answer performance. Again, you will see that at class 5, more proportion of students have given the correct answer, which has reduced in class 6 and then significantly increased in class 7. It's very interesting. Why is it that class 6 students have performed not better than class 5, which is something naturally one would expect, but that's not happening, right? This is an interesting graph. All right, we'll see one more question. A rectangular piece of paper is cut out of a bigger rectangular sheet of paper as shown below. Which of the following is true about shape 1 and shape 2? All right, we know that some portion is cut, so therefore area will definitely decrease. But what happens to the perimeter? If you see, this part was originally part of perimeter, which is now this part equal to this part, and this part is equal to this part. So perimeter has not changed, whereas area has decreased. Correct answer is option A, perimeter is same, but area is different. But 51%, that means more than half of the students think that both the area and perimeter are different. Why is this happening? They are correlating area and perimeter. Area has decreased, so perimeter also has decreased. If area increases, perimeter will also increase. Another major misconception that we have seen among students is they think that larger the area of a shape, greater is the perimeter, and smaller the area, smaller is the perimeter. Is this true? No, this is a misconception. Now, as a teacher, what can we do in our classes? As simple as this, we will see what exactly is this. As simple as this, something like this can be done to make them realize that area and perimeter have no such relationship. For example, we'll keep the first figure P constant, same, will not vary it, but we will try to vary Q so that we exhaust all 4 cases. For example, we'll first make them find the area and perimeter of both P and Q. Now, in the second case, what we have done is this tile has been shifted here. Now, what happens to the area? Nothing has changed in the area. Area remains the same. But you can make them calculate the perimeter of this figure to make them see whether it has increased or decreased. And then in the third case, we have increased the area. This was missing here. Area has been increased. But what happens to the perimeter? Make them calculate. And in the fourth shape, again, this to the tile from here and here have been shifted to this. So what happens to the area? What happens to the perimeter? This is a question from our Mindspark, AI Mindspark question. This is actually an interactive where students can interact with the system. I mean, there is a drop down, they can click on it and they can answer the question. All right. Moving to the next question. Take a look at the question on the slide. A cuboid is cut in the middle to form two smaller cubes as shown in the figure below. What can we say about the sum of the surface areas of the two cubes as compared to the surface area of the cuboid? Now, we all know that there is an extra surface exposed when the cuboid is cut. That is this surface and this, the one hiding behind. So the surface area will obviously increase. That is, it will be more. Second option. But 38.4 students think that the sum of the surface area will remain the same. Now, what could have led to this? So it could be two reasons. One, they have overgeneralized the concept of area that they have learned in case of 2D shapes here as well. Because in 2D, if you tear a paper, the area will not increase, will remain the same. But in 3D, it has an effect on the surface area that they have not understood. Secondly, what could have led is the conservation of volume is getting is interfering in this case, because when a cuboid is cut, even before cutting, it had a volume, it was occupying a certain volume, and even after cutting, it is occupying the same amount of volume. That is, volume is conserved. This is interfering in identifying what happens to the surface area, right? So these are some of the misconceptions that, I mean, there are much more, there are hundreds of them, but we could cover some of them at least that we have seen in asset papers and along with the performance data. Now, in the next segment, Maulik will take us through some teaching strategies that we can follow in classrooms so that these misconceptions are A, prevented, B, remediated. Over to you, Maulik. Thank you.
Thanks, Diksha. There is some technical lag on my end while it goes into presentation mode. Till then, I just want to tell you that it is important to diagnose this misconception well, right? How do you do that? We need good questions. You already saw a lot of good questions. You will often see if you have taken EI asset and cares, they are part of the reports. So, yeah. Diksha, maybe it's okay if you can present it at your end.
Yes.
We often find taking these questions to classroom, asking students justify their answer, that helps to understand misconceptions, what they have in their mind. They will also understand that they seem to have faulty understanding of they seem to have faulty understanding at their end as well. Then engaging in a dialogue where students can debate, discuss, get into productive struggle often helps them with remediation. So, yeah. Let me try once again.
Yeah, Maulik, I just started sharing.
Okay, great.
Is my screen visible?
Not the presentation slide, Diksha.
Okay, let me share again.
Another thing we could do is think about the root causes of the misconceptions. We saw overgeneralization. Yeah, thanks, Diksha. We can see it now.
Okay.
We can also notice repeating patterns of errors in answer scripts. We can do student interviews like we saw in the length measurement video, right? We asked students to justify their answer. And that gives maximum insights as to where these underlying beliefs are and help us understand the root causes. Once we do that, knowing about them will help us proactively plan our lessons and effectively deliver instructions, because now we know in case of ruler measurement, we'll not just expose students to one type of questions, one type of scenario. We'll also share examples and non-examples. Can you move to next slide? Yeah, next. So explicitly warn students about these misconceptions may be not an effective strategy. Make students aware about their errors. How? Engaging them in productive struggle with questions like this and do an interview. Ask them to justify their answer, share a rationale. Another strategy could be giving examples and non-examples. Ask Most importantly, we should try and understand how can we nip the problem in the bud. That is, when we expose students to the concept itself, how we can expose them in a way that those misconceptions do not arise. Yes, next one. For example, in the case of the question on ruler measurement, the underlying root cause is not counting 1 centimeter gaps. Also, they're not understanding the core idea. All measurement is actually a comparison. Comparison with respect to reference unit, with respect to standard units, right? That's the underlying notion about any measurement concept, be it weight, capacity, area, surface area, volume. When we say area is 10 centimeter, 10 square centimeter, we are essentially saying it is 10 times the area that is taken by 1 unit square of side 1 centimeter. That is the underlying idea that we need to keep reiterate whenever we teach any measurement concept. Next one. So we apply this understanding in Mindspark content as well. And you could also do the same. We have been finding it successful. So here measurement is about comparison. It is about reiteration of iterating units from non-standard to standard. Next one. We also have a entire module where students are made to construct their own ruler, which is what you can also do in classroom. Give them 1 centimeter object and say, now construct your own ruler through a paper strip. And then use that to measure length of objects. Ask them to place object at anywhere on a scale and still measure the length. For example, the question on the screen. That will reinforce the idea of counting 1 centimeter gaps. Next one. So in animations, we also showcase counting of 1 centimeter gaps in case of Mindspark questions, and we reiterate that understanding. Next one. Now, this is what is called proactive teaching. We teach angle as amount of turn and reiterate that idea throughout the module that we have in EI Mindspark. In case of protractor, which is angle measurement, you don't jump to measuring using protractor directly. We strengthen the idea that the angle in blue portion is 5 times the unit angle, which is of 10-degree measure over here. So the idea is iteration is reiterated. Now equal sign needs to be exposed as relational operator right from the beginning. We teach equal sign as is the same as. And then we have examples and non-examples, and we give exposure to variety of questions on equal sign. Next one. Move to the next slide. Yeah, you can also do student interview and dialogue as we had already talked earlier. Bring these questions which elicits productive struggle. Ask them to share rationale, why this shape is not half, why this shape is not 1/4, and things like that. Next one. Yeah, whenever we are teaching procedural algorithm, get into why this procedure works. That is what we do in Mindspark. And that is what we find it meaningful. Here, students need to understand the need to make the denominator the same. And that is what is done through series of questions like these on screen. They are made to explore on their own, that they have to have, they need common denominator. Here they can see the sum is same as half, which is the fraction of the circle colored. And to find why it is half, they can see the divisions equal, the shape needs to be divided into equal parts, which is 6. That is common denominator, common multiple of 3 and 6. Next one. Yeah, so this is what we allow exploration. Let them try and find out how many equal sides, equal parts the shape needs to be divided into, so that they can find out the fraction of the shape colored, which is the sum. Technology allows us to do that. To summarize, asking good non-routine questions often help diagnose learning gaps and misconceptions. Call for action is take them to classroom, generate insights, and use these insights. Incorrect answering is not always about a careless error or a slip. Students have strong rational, and that is what we say misconceptions. Alternate misconceptions, alternate conceptions or misconceptions may come in a way of learning new concepts, and often they persist beyond grades. And hence, the best strategy is to nip the problem in the bud, right when you are teaching, right when creating lesson plans, factor that in, and that will make your instructions effective. Do understand the root causes. Remember, reteaching is not effective. That doesn't necessarily help remediate a misconception when students continue to have. So through EI Asset and EI Cares, we have been helping teachers diagnose the misconceptions and share their extent. Please make best use of that. EI Mindspark has consumed insights of uh, misconceptions students have that got elicited through EI Asset and EI Cares, and it is aimed at building conceptual understanding and overcoming misconceptions. You could also apply similar strategies in your classroom instructions. Let us make this shift to happen to prepare our students for better careers. Assessment is not of learning. Assessment equals learning. Scan this feedback form and please fill it up. Thank you for being with us for an hour. You can also find the feedback link in chat message. Alternatively, you can share, scan from your mobile, from any of the payment apps as well, like Paytm. Once you have filled the feedback form, feel free to leave the webinar. In case you have any questions, please put it in Q&A. Please fill up the feedback form. Please ensure you enter right details. The certificate of participation will automatically be mailed to you. Please share your key takeaways, reflect while filling up the feedback form. Feel free to leave the webinar once you do not have any questions to ask us. You can fill up the feedback form. Feel free to leave this webinar. We are here for next 1 or 2 minutes in case you have any questions. Thank you all 100 participants who have filled up the form. Your certificates are already sent. Your feedback is valuable. Please enter your key takeaways as well. Hope you enjoyed and learned a lot from this session. You'll always find it interesting to take these questions into classroom and engage students with them.